My name is Ken Wells. I'm a product applications engineer. I live in Philadelphia, Pennsylvania, and I'd like to welcome you to our discussion today about how to calculate duty. This is both in heat exchangers and in furnaces, and this will center on British units. Thank you. So let's start about the definition of heat exchanger duty. Very simply, heat exchanger duty is the rate of heat that is moved from the hot stream to the cold stream. Of course, based on the laws of thermodynamics, heat always moves from the hot side to the cold side. We need to understand the ins and outs of calculating duty on a heat exchanger, even though most of the time in the future, once you get this understanding in your head, we will be doing this with Excel or with a model like HX Cool Pro or HXNet. Most of the time in United States refineries, we will be dealing with British engineering units, and the duty is expressed in millions of BTUs per hour. There's a slightly different definition that we want to touch on. It's a bit confusing, so we thought I'd put it out here at the beginning, and that's a furnace duty. So you'll hear these terms bandied about, whether it's furnace duty or heat exchanger duty, and we think you need to know the difference. So furnace duty, fire duty in a furnace is the amount of combustion heat liberated in the furnace calculated from the value of the fuel gas that's put in. The absorbed duty, on the other hand, is the amount of heat that the cold stream gets from that firing. And that's going to be calculated by some of the calculations that we're going to discuss in the future. Important term to remember is that furnace efficiency, in one way to describe that, is the absorbed duty. That is the amount that's absorbed by the cold stream, that the cold stream captures, divided by the fire duty, the amount that the hot stream or the furnace puts out. So here's some really important stuff. Duty can be calculated on the hot stream and on the cold stream of any given heat exchanger. Theoretically, the hot side duty always equals the cold side duty. The ratio between the hot side and the cold side duty is called exchanger heat balance. If it's not reasonably close to 100,000 or 100%, there's something wrong. Either there's a measurement error, or the stream is being partially bypassed, and that could be happening because there's DP issues in the heat train, or there is unaccounted vaporization or condensation. So anytime the hot side and the cold side don't agree with each other, there's something going on. Another thing that's really important is that all of our duty calculations that we're going to be talking about in the coming slides are in weight. Typically, and for the purposes of this discussion, in pounds per hour, not in volume or in barrels per day. This is an artifact of the way refineries do their calculations. Heat exchange calculations are always in pounds per hour, so we're always going to be dealing with that. There are two kinds of duty: sensible heat and latent heat. Sensible heat is that amount that is measured by temperature change or simply by a thermometer. So we have a pound of water and it heats up from room temperature to 212 degrees. That is sensible heat. Latent heat, on the other hand, is heat that is associated with a phase change, vaporization, or condensation. And that is something that's much harder to figure out and something that's much harder to measure. So let's keep those two things in mind as we go through these calculations: sensible heat versus latent heat. Here's the equation that hopefully you've seen in the past. It's called the duty equation. It's for sensible heat only, and it's sometimes abbreviated almost as a rhyme as MC sub P delta T. So Q, which is a rate of heat transfer, is a function of the mass flow rate, M, times the specific heat times the change in temperature for that stream. Okay, we're going to put it in color and we're going to talk about the units here. So Q is a rate. That's the heat transfer rate, and it's typically in BTUs per hour, or as I said earlier, millions of BTUs per hour, just for the comfort of the numbers. AM needs to be calculated in pounds. As I stated before, most measurements in refineries are in volume flow rate rather than pounds flow rate, so we need to do a conversion there, and sometimes that can be tricky. CP is the heat capacity. That's the amount of heat that's required to change 1 pound of the fluid from across 1 degree Fahrenheit. And delta T is the temperature change across that. The purpose of this slide is dimensional analysis to illustrate that Q calculated in BTUs per hour with MC sub P delta T. If you do the dimensional analysis, you can see that all the dimensions cross out and we're left in BTUs per hour for Q. What's really important here is that if you really stop to figure out the units that are available for each of the components in this calculation, it helps you understand the basis of the calculation. So pounds per hour times BTUs per pound per degree Fahrenheit times degree Fahrenheit gives you BTUs per hour. I want to keep reminding you, I'm going to keep reminding you that there's a second component to the Q, and that is the latent heat. I may have mentioned before that we neglect latent heat far too often. So in addition to the MC sub P delta T, there is a latent heat component of the Q. That is a different M, because not all of the stream may vaporize or condense, but it's a different M times the heat of vaporization for that M. So, and we're going to cover that a lot more. Here's some very generalized constants that are used in the calculations, the equations that we just talked about. And what I want to highlight here is the difference between water and hydrocarbon. So, for instance, water has a specific gravity of 1 by definition. Water has a heat capacity of 1 by definition, and water has a heat of vaporization, which we're going to get into in depth in a little bit, of almost 1,000 BTUs per pound. So water is very dense thermally, as a way to think of it. The two other streams that I have described here, isobutane and crude oil. Isobutane because that's going to be part of our example that we're going to go to in depth, and crude oil have very different heat capacities and heats of vaporization. So the heat capacity is typically about a half of what water is. So it takes only half as much heat to raise up a pound of isobutane or a pound of a hydrocarbon to a higher temperature than it does of water. And it takes only about 1/6 as much heat to vaporize a pound of a hydrocarbon as it does to vaporize a pound of water. So that kind of explains why water is used as a heat transfer medium, both in cooling water and in condensing steam. Another thing I wanted to mention here is that we have to be really careful on the rightmost column here. When we're talking about crude oil, we're talking about a mixture, and most everything we do in a refinery is based on a mixture. We have to be really careful about putting a single value on a heat capacity, a heat of vaporization, a density, anything that's associated with a mixture, especially if it's a very wide mixture like crude oil is. In addition to the components of a mixture, the temperature and pressure of a mixture determine some of the properties, and this graph is just meant to show that heat capacity varies by a significant amount, almost 50%, over the normal range of crude oil heat capacity that we would be calculating for the heat exchangers that we consider. So we need to make really sure that we're using the right heat capacity that's relevant for the temperature that we're talking about even if we're not dealing with vaporization. Okay, for the next couple slides, we're going to talk a lot, probably more than you ever want to hear, about the E20s. And this is a simple heat exchanger, but it includes a lot of the calculations that we want to go into about duty. It is a DIB overhead condenser, so isobutane is the single component in the overhead stream, which is shown in red here, going through at about 37,500 barrels per day, being cooled from 128 to 120 degrees Fahrenheit, but also condensing. We are using 2,800 gallons per minute of water to cool that stream off, and then in the process of doing that, the water heats up from 85 degrees to 115 degrees. One of the reasons I picked this is there's a lot of unit calculations, unit conversions that I want you to understand as we go through these. We'll start with the easy stuff, the amount of heat that the cold side picks up. Cooling water hopefully has only sensible heat, and its heat capacity is 1 by definition. We do have to deal with the unit conversion, so we're going to go through with that. And we have once again, our rhyme, our MC sub P delta T to get to Q. So our M starts with a volume flow of 2850 GPM. Various conversions, including the specific gravity, the parts of the British system, which are British engineering units, which are kind of strange, which are the weight of water in pounds per gallon and the number of gallons in a barrel. That conversion takes us to 2850 GPM, means 1,424,000 and change pounds per hour. And remember, for any kind of duty calculation, we're always talking about pounds per hour. The heat capacity for water is pretty simple here. It's 1 pound one BTU per pound per degree Fahrenheit, and that is by reverse definition. The delta T, temperature in and out, measured, that's about 30 degrees. So MC sub P delta T equals 42,733,000 by rounding of BTUs per hour. And as we remember, that's a rate. Okay, and towards the bottom of the screen, you'll see that we would express that typically as 42.7 BTUs per hour if we were talking to a process engineer in a refinery. Okay, here's the same exchanger again. Just to review, now we're going to talk about the hot side, which is isobutane coming in at 28 degrees Fahrenheit as a vapor and cooling off, coming in at 128 degrees Fahrenheit as a vapor and cooling off to 120 degrees, but it's also condensing from a vaporous isobutane to a liquid isobutane, and there's almost 38,000 barrels per day coming through there. So here's the calculation for that sensible heat. Okay, as you'll note, as we mentioned before, the pounds per hour is different because we have a different density. We are recorded in barrels per day here instead of GPM, so the conversions are a little different, but we come up with 320,000 pounds per hour. Different heat capacity, much lower. Delta T also much lower, so we end up with just about 1 million BTUs per hour of sensible heat change, and this is pretty low compared to the almost 43 million BTUs per hour we had earlier. So what went wrong here? What went wrong is there's a lot of latent heat in any condenser. So this calculation shows that in addition to the MC sub P delta T, we need to take into account the heat of vaporization, or in this case condensation, of the isobutane stream. We need to know the pounds condensed or evaporated, and we need to know the heat of vaporization in BTUs per pound. So clearly the difference between latent heat and sensible heat is important to me. So what we're going to do now is take a look at a demonstration with it using a tea kettle to explain that. We've got 1 pound or 16 ounces of water that we're going to heat up. Obviously I've sped up this video and we can see the water heating at a fairly steady rate towards the boiling point of water. Going to capture these numbers in a minute to do the calculation that tells us how much heat is being added and the difference between latent and sensible heat. Right now we're obviously still adding sensible heat. And now we can hear the production of steam, which says that we are adding latent heat. Anybody who knows me knows I like to make graphs. So here's a graph of what we just saw. Time in seconds versus temperature, water temperature. And we can see two different spots in the curve. The kettle steadily heating up over time from about 70 degrees ambient temperature up to the boiling point of water. And then once steam started to be made, the temperature stayed steady and steam was heard coming out of the kettle. So just to emphasize once again, latent heat is important. That's what's shown in the red here, but the black, the sensible heat is also important. So we're going to go through those calculations for the tea kettle. Okay, we want to realize that this is a semi-batch operation, and everything in a refinery is a continuous basis. Another big difference here is this is a pure substance. Boilers have pure substances in refineries, but most of the time in a refinery, things are a complex mixture. So what we have to do to get these numbers to a rate is to get them per hour, which is the way we do duty calculations anyway. So M as a flow rate over 36 seconds for 1 pound, which we saw is the amount of water that I put in, the amount of hours. Heat capacity, again, is easy for water. That is 1 BTU per pound per degree Fahrenheit. The temperature change over the course of the 36 seconds that we ran the tea kettle is from 72 to 211 degrees. It's 138 degrees. That gives, because it's a pound of water, that gives simply by math 138 BTUs, and divided by the fact that it was well less than an hour, that's about 13,000 or almost 14,000 BTUs per hour. After that time, I let the tea kettle boil for another 36 seconds. I looked up the latent heat for water at atmospheric pressure. It's 970 BTUs per pound. And based on the weight that we saw between the two weighings, we lost about 2.29 ounces, and that gives a firing rate of about 13.7 13.7 thousand BTUs per hour. What's really important for you to realize here, besides the fact that these two numbers agree, in other words, the firing rate or the boil-up rate was the same, for the first half of this experiment, the heat went into raising the temperature of the water. For the second half of this experiment, the heat went into vaporizing the water. The other thing is the difference in the size of a tea kettle versus a refinery. So a typical refinery exchanger would have around 10 million BTUs per hour. This tea kettle has 0.01 BTUs per hour. So that's a pretty simple calculation, the one both we saw for the E20s and the one we're about to see for the tea kettle, and that is how much water evaporates. In the case of the tea kettle, we just measured it in the by weight difference. In the case of the E20, we know that 100% of the isobutane has condensed. So for simple systems where there's 100% condensation of one substance, or we have something like, say, a steam meter, we can calculate in Excel, we can calculate the latent heat. However, most systems in a refinery are complicated, and we need to use a flash model. This would be overhead condensers of a mixture, like a crude overhead or an FCC main fractionator overhead. And we have to, when we do that kind of calculation, we need to include the fact that there's stripping steam in that mixture, and it's an important portion of the duty and an important portion of the flash calculation. Finally, we also have an important hydrotreaters, feed effluent exchangers, that have vaporization and, on the feed side and condensation on the effluent side in the presence of a large amount of treat gas. So those calculations are really important. It needs to be said that those aren't things that we're capable of doing within Excel. We need to use a flash model. HX Cool Pro does that for you. Our customers will use Aspen or some other simulation program to do the same thing. One of the reasons we've talked about the various constants that we use is to make sure that we can compare apples to apples with our process engineering customers when we talk about the results. So if we're trying to tease out why our numbers are a little different from theirs, we want to know the area of the exchanger, we want to know the heat capacity that we've used, we want to be able to discuss those in depth. Here's our E20s again, and we're going to go back to calculating the latent heat there. So just like the tea kettle, if we want to do a single substance latent heat, we can look at the amount of heat condensed, the latent heat for that per pound for that substance, and multiply it out. So it's fairly simple when we have a 100% condensation, and that gives us the balance of the heat in the E20s, and it balances out at both at about 43 million BTUs per hour. So when we don't have a simple situation, when we don't have 100% condensation or a simple situation like just water, what do we do? To make those accurate calculations, we need a distillation curve for the mixture, whether it's crude overhead naphtha or NHT feed or distillate hydrotreater feed. We need the system pressure, and we need to interpolate those system pressures at the spot where the condensation or vaporization is happening. And of course, the amount of treat gas, which is an enormous percentage of the volume flow needs to be included because that changes the partial pressure of all of these substances. So that's something that we're not capable of doing by ourselves in Excel. We need to use a model like HX Cool Pro to figure that out. As promised, we're moving on to our last component, or our last portion of duty, and that's a fire duty in a furnace. And this is really different. Although there's portions when we're looking at a furnace, we're looking at the absorb duty, which is the same as what we just calculated. We want to compare that often to the fire duty. Fire duty is the calculation from the combustion of the fuel gas instead of MC sub P delta T, or MC sub P delta T plus any vaporization that's taking place. So we need to look at the fuel gas rate and the fuel gas quality to figure out the amount of heat that's liberated when this is burned. There's two fuel gas heat values. Refinery would almost always use the LHV, which is the lower heat value, which assumes that all of the water vapor that's formed as a combustion product leaves as a vapor in the fuel gas. If you have a super efficient natural gas heater at home, that will use a larger heat exchanger for the flue gas, and it will allow the water that's in the flue gas to condense so that you're not exhausting that steam, but instead you are capturing that latent heat of the water. That's not practical in a refinery, so in all cases we use the LHV, and that's what would be reported here. Here's a diagram of a fire duty, and I've done this with both the absorbed and the fire duty. So in the orange, the fire duty takes the fuel gas rate, multiplies it by the fuel gas heating value, and comes up with a fire duty. Pretty easy calculation. You'll want to check with your process engineer to make sure that you have your million and your 1,000 scuffs correct. You don't want to, and you will be off. If you're off by a factor of 1,000. So you'll want to check with that. On the absorbed duty side, you'll, in this case, I have used just MC sub P delta T. That's not always correct. In some time, depending on the furnace, that could be very wrong. So we want to consider vaporization in the furnace also. Here's our final calculation. I'm going to really skip over this quickly because this is our study group question for next week, where we will be calculating the duty on the heat exchange train, the duty on the furnace, and the fire duty on the furnace. So look forward to talking to you folks at the end of that time. Thank you.